Spring, 1942. Southwest Pacific. A North American B-25 Mitchell medium bomber lies in twisted wreckage across a jungle clearing, its crew, having abandoned the aircraft after mechanical failure, forced an emergency landing behind Japanese lines. Among the bomber's equipment, still secured in its mounting brackets in the nose section, sits a 50-pound mechanism of extraordinary complexity. 2,000 precisely machined parts, gyroscopes spinning on jeweled bearings, an analog computer capable of calculating bomb trajectories in real time. The Norden Bombsight, America's most closely guarded aviation secret. Within weeks, Japanese recovery teams would locate this wreckage and dozens of similar sites scattered across newly conquered territories. What they would discover in examining these captured instruments would reveal an industrial gap far wider than anyone in Tokyo had imagined. The Norden Bombsight represented not just advanced technology, but an entire philosophy of precision manufacturing that Japanese industry had never achieved. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The device itself embodied principles that seemed almost impossible. A bombardier could input altitude, airspeed, and wind conditions. The mechanical computer would continuously recalculate the bomb's impact point as flight conditions changed. The bombsight connected directly to the bomber's autopilot, flying the aircraft with greater precision than any human pilot during the final approach. In testing under ideal conditions, the Norden had demonstrated accuracy within 75 feet from altitudes exceeding 20,000 feet. This performance, if achievable in combat, would revolutionize strategic bombing. American security surrounding the Norden bordered on obsession. Bombardiers swore oaths to defend the device with their lives if necessary. Before and after each mission, armed guards transported the bombsights between aircraft and secure vaults. If forced to bail out or crash land in enemy territory, crew members carried specific instructions. Fire 2 rounds from a .45 caliber pistol into the rate mechanism, 1 round through the telescope. If time permitted, a thermite grenade would melt the entire assembly into an unrecognizable lump of metal. These precautions reflected genuine concern. The United States had invested over $1 billion in Norden bombsight development and production by 1942, roughly half the cost of the Manhattan Project. Military planners believed the device would prove decisive in the strategic bombing campaign they were planning against both Germany and Japan. Loss of even a single intact example to enemy hands represented a potential strategic disaster. Yet, by mid-1942, Japanese forces had captured multiple Norden bombsights, primarily from downed B-25 Mitchell bombers operating in the Southwest Pacific. The Doolittle raid on Tokyo in April 1942 had deliberately excluded Norden bombsights from the participating B-25 seconds for precisely this reason. Captain Ross Greening had designed a simple 20-cent replacement sight specifically to prevent the Norden from falling into Japanese hands if any aircraft were captured. Despite these precautions, subsequent B-25 operations throughout the Pacific provided Japanese engineers with several intact examples. The examination began at technical facilities near Tokyo, where Japan's most skilled aeronautical engineers gathered to assess American bombing technology. They approached the task systematically, photographing every component, measuring every dimension, documenting every mechanism. The Norden consisted of 2 primary assemblies. The gyroscopic stabilization platform maintained a level reference regardless of the bomber's movement. The mechanical calculator and sighting head computed trajectories and aimed the bombs. These assemblies connected through a complex optical system, with the eyepiece positioned awkwardly between them, requiring considerable dexterity to operate effectively. What impressed Japanese engineers most was not the basic concept, which they understood, but the precision of execution. Every gear meshed perfectly. Every bearing spun without perceptible friction. Every adjustment mechanism operated smoothly through its full range of motion. The gyroscopes, spinning at thousands of revolutions per minute on jeweled bearings, maintained perfect balance. The optical system featured ground glass elements of exceptional clarity. The mechanical computer used wheel and disc calculators machined to tolerances measured in thousandths of an inch. Japanese engineers possessed the theoretical knowledge to build such a device. They understood gyroscopic stabilization, having developed their own gyro-stabilized systems for naval applications. They comprehended the mathematics of ballistic trajectories and the principles of analog computation. What they lacked was the manufacturing infrastructure to produce these components at the precision the Norden required. The decision was made to attempt reverse engineering. Japanese industry would build a simplified copy, eliminating features deemed too complex while retaining the Norden's core functionality. Engineers designated the project the Type 4 automatic bombing sight. Development began in 1942, with the goal of equipping Japanese heavy bombers with precision bombing capability, matching American standards. The attempt revealed fundamental limitations immediately. The gyroscopes required precision that Japanese bearing manufacturers could not consistently achieve. The mechanical computer demanded gear-cutting accuracy beyond what most Japanese machine shops could deliver. The optical elements needed glass grinding techniques that few Japanese optical firms had mastered. Each component presented manufacturing challenges that proved surprisingly difficult to overcome. Japanese industry had organized itself around different principles than American mass production. Skilled craftsmen hand-fitted components to achieve required tolerances. Master machinists adjusted parts individually until they functioned correctly. This approach worked adequately for producing hundreds of aircraft. It failed completely when attempting to manufacture thousands of precision bomb sights with interchangeable parts. The Type 4 development program struggled through 1943 and into 1944. Prototype units functioned, but barely. Gyroscopes drifted, requiring constant recalibration. Gears wore rapidly under operational stress. Optical elements fogged in temperature extremes. The mechanical computer produced inconsistent results. Most critically, manufacturing costs proved prohibitive. Each Type 4 bomb sight required hundreds of man-hours from skilled workers who were desperately needed for other war production. By late 1944, Japanese engineers acknowledged defeat. The Type 4 automatic bombing sight was too complex to mass-produce given existing industrial capabilities. A drastically simplified alternative, designated the Type 1 Model 2 automatic bombing sight, entered limited production in early 1945. This version eliminated most of the Norden's sophisticated features, retaining only basic gyroscopic stabilization and simplified trajectory calculation. Approximately 20 units entered service before the war ended. Japanese bombardiers who used these simplified sights found them marginally better than manual bombing methods, but nowhere near the Norden's capabilities. The failure extended beyond simple copying difficulties. Japanese engineers examining the Norden had encountered proof that American industry operated on fundamentally different principles. The bomb sight's construction demonstrated mass production techniques that Japanese factories had never implemented. Parts showed identical machining patterns across multiple units, indicating automated production from master tooling rather than individual craftsmanship. Tolerances remained consistent throughout entire production runs. Components from different bomb sights proved genuinely interchangeable without adjustment or fitting. This level of standardization required manufacturing precision that Japanese industry had not prioritized. Before the war, Japan had excelled at producing high-quality individual items through skilled craftsmanship. What Japan lacked was the infrastructure for producing millions of precisely identical parts. American industry had developed this capability through decades of automobile manufacturing, where interchangeable parts and assembly line production had become standard practice. Japanese industry, with its limited domestic automobile market and emphasis on skilled labor, had never developed comparable mass production systems. The Norden also revealed how American engineering approached complexity differently than Japanese design philosophy. American engineers had created a device specifically intended for operation by personnel with standardized training. The bombardier needed mechanical aptitude and careful instruction, but not years of specialized experience. Japanese equipment typically demanded expert operators who understood their systems intimately and could compensate for quirks and limitations through skill and experience. This difference reflected deeper organizational assumptions. American military planners expected to train hundreds of thousands of airmen rapidly, equipping them with standardized systems that worked reliably without requiring specialized expertise. Japanese military culture valued the highly trained specialist who could extract maximum performance from equipment through superior technique. The Norden embodied American industrial democracy, building sophisticated capability into the machine itself so that average personnel could achieve excellent results. Japanese equipment reflected traditional values, assuming that skilled operators mattered more than automated systems. The strategic implications became painfully clear as the war progressed. American factories produced over 90,000 aircraft in 1944 alone. Japan struggled to build 28,000. But the disparity in numbers understated the real gap. Each American aircraft contained thousands of precisely manufactured interchangeable parts, could be maintained by mechanics with basic training using standardized replacement components, and could be repaired quickly in field conditions. Japanese aircraft required skilled technicians for maintenance, specialized parts for repairs, and constant adjustment to remain operational. The Norden Bombsight served as a microcosm of these larger industrial differences. American bombardiers, after several months of training, could operate the device effectively. Maintenance crews could replace major assemblies using simple tools and standard procedures. The bombsight continued functioning under conditions that would have disabled hand-fitted Japanese equipment. This reliability came not from superior materials or better theoretical design, but from superior manufacturing processes that built precision into every component. Japanese attempts to copy the Norden failed not because Japanese engineers lacked ability or understanding, but because Japanese industry lacked the organizational structure to implement American mass production principles. Changing this would have required transforming Japan's entire industrial base, retraining millions of workers, investing in new manufacturing equipment, and abandoning traditional craftsman-based production methods. The war provided neither the time nor the resources for such fundamental reorganization. By 1945, as American B-29 superfortresses appeared over Japan carrying Norden bombsights vastly improved from the original models captured 3 years earlier. Japanese engineers understood what those captured instruments had been trying to teach them. Modern industrial warfare was won not by superior craftsmanship, but by superior production systems, not by building better individual weapons, but by building adequate weapons in overwhelming numbers, not by skilled workers, but by systematic processes that enabled ordinary workers to produce precisely manufactured products rapidly. The captured Norden bombsights that Japanese engineers had examined so carefully represented more than advanced technology. They embodied an entire industrial philosophy that had taken American manufacturing decades to develop. The precision that impressed Japanese engineers so profoundly came not from the skill of individual American workers, but from production systems designed to eliminate the need for individual skill by building quality into the manufacturing process itself. After Japan's surrender in August 1945, American occupation authorities banned aircraft manufacturing and research. This prohibition would last until 1952. When Japanese industry finally returned to aviation, it would do so having learned the lessons those captured Norden bombsights had taught. The post-war transformation of Japanese manufacturing, from craftsman-based production to systematic mass production, would eventually make Japan a global leader in precision manufacturing and quality control. But during the war, those lessons came too late. The Type 4 automatic bombing sight, Japan's attempt to copy the Norden, stood as testament to the industrial gap that had doomed Japan from the moment it chose to fight a war of production against the United States. The American bombardiers flying over Japan in 1945 carried Norden bombsights that their counterparts could aim with confidence, knowing that American industry would replace any losses faster than Japan could shoot them down. The captured instruments that Japanese engineers had examined, measured, and attempted to reproduce had revealed a truth that no amount of courage or determination could overcome. Japan had entered a war of industrial attrition against an opponent with 10 times its manufacturing capacity and fundamentally superior production methods. The failure to successfully copy the Norden bombsight was not the cause of Japan's defeat, but it perfectly illustrated the industrial inadequacy that made that defeat inevitable. The stark reality became undeniable when Japanese engineers compared their own bombing systems to what they had discovered in the captured Nordens. Japanese horizontal bombers relied on manual bombsights that required extensive calculations by the bombardier during the approach. The Type 89 bombsight used by the Imperial Japanese Navy demanded that the bombardier manually adjust for wind drift, while simultaneously coordinating with the pilot for course corrections. The process required considerable skill and consumed precious seconds during which the bomber had to maintain straight and level flight, exposing itself to anti-aircraft fire. The Norden automated most of these calculations and, critically, took control of the aircraft during the bomb run. Once the bombardier acquired the target and engaged the autopilot coupling, the bombsight itself flew the bomber with precision no human pilot could match. This freed the bombardier to focus solely on maintaining target acquisition and monitoring the automated drop sequence. The difference was not merely convenience, it represented a fundamental advantage in both accuracy and survivability. Japanese test pilots who flew captured B-25 seconds equipped with Norden bombsights reported the experience with a mixture of admiration and frustration. The system worked exactly as American training manuals described. Set the altitude, input the bomb ballistics, acquire the target, engage the autopilot. The bomber would align itself, compensate for wind drift, and release bombs at the optimal moment. The entire process felt almost effortless compared to the intense concentration and constant communication required with Japanese equipment. But replicating this capability proved impossible with available industrial resources. The autopilot interface alone presented insurmountable challenges. The Norden's automatic flight control equipment represented a sophisticated electromechanical system that had taken American engineers years to perfect. It required precision servo motors, reliable electrical systems, and fail-safe mechanical linkages that could safely control an aircraft weighing tens of thousands of pounds. Japanese industry could build individual prototype systems, but mass-producing them with consistent reliability exceeded manufacturing capabilities. The gyroscopes presented their own special difficulties. The Norden used precision gyroscopes that maintained stability through extended missions, despite extreme temperature variations, vibration, and the G-forces of combat maneuvering. These instruments required jeweled bearings ground to tolerances of 10,000ths of an inch, housed in sealed assemblies that excluded moisture and contamination. Japanese optical instrument makers could produce such bearings in small quantities for laboratory equipment. Producing thousands for field equipment proved economically unfeasible. Temperature management represented another critical challenge that Japanese engineers had underestimated. At bombing altitudes above 20,000 feet, temperatures regularly dropped to -20 degrees Fahrenheit or lower. The Norden's designers had anticipated this, specifying lubricants that remained fluid at extreme cold and using materials with matched thermal expansion coefficients to prevent binding as temperatures changed. American bomber crews used electrically heated blankets to keep the bombsights warm before the bomb run, but the devices functioned reliably even when partially frozen. Japanese copies experienced constant problems with cold weather operation. Lubricants congealed, moving parts bound, optical elements fogged, gyroscopes lost stability. Each problem could be addressed individually through careful selection of materials and specialized treatments. But implementing all necessary modifications simultaneously, while maintaining the precision required for the system to function, demanded manufacturing sophistication that Japanese factories operating under wartime conditions simply could not provide. The contrast became even more painful when Japanese intelligence obtained information about American production numbers. By mid-1943, the Norden Company's main plant in New York City had transformed from a small engineering laboratory into a major manufacturing facility producing bombsights by the hundreds each month. Two additional manufacturers, Lucas Harold Corporation and Victor Adding Machine Company, had received contracts to produce Norden components, multiplying American production capacity far beyond what any Japanese facility could achieve. These American factories employed tens of thousands of workers, many of them women with minimal mechanical experience before the war. yet they produced bomb sights that met exacting specifications through the use of precision tooling, automated inspection equipment, and systematic quality control procedures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The production line approach meant that each bomb sight was constructed from components manufactured to identical specifications, tested at multiple stages of assembly, and calibrated using standardized procedures. Workers needed training and discipline, but not years of apprenticeship in precision instrument making. Japanese instrument production remained concentrated in small workshops, where master craftsmen supervised small teams of skilled workers. These shops produced excellent results when building individual units or small batches. They could not transition to mass production without abandoning the very craftsmanship that made their work valuable. The cultural resistance to this transformation ran deep. Japanese industry had developed over centuries around the concept of the skilled artisan perfecting his craft through dedicated practice. American industry had evolved around the concept of the interchangeable worker performing standardized tasks with mechanical aids. Neither approach was inherently superior in peacetime, but in total war, where production capacity directly determined military outcomes, the American system possessed decisive advantages. A factory could train a new worker to assemble Norden bombsights in weeks. Training a craftsman to hand-fit precision instruments required years. When American factories lost workers to military service, they replaced them rapidly. When Japanese workshops lost skilled workers, production suffered immediate and lasting damage. The bombing campaign against Japanese industry, which intensified through 1944 and into 1945, magnified these vulnerabilities. American strategic bombing targeted the supplier networks that Japanese aircraft manufacturers depended upon for specialized components. Small machine shops that produced precision gears or optical elements could not easily relocate or rebuild after being destroyed. The loss of a few key suppliers could halt production at multiple final assembly plants. By contrast, American production capacity proved remarkably resistant to disruption. When German U-boats threatened Atlantic shipping, American factories shifted to domestic suppliers. When strategic materials became scarce, engineers redesigned products to use alternatives. The vast scale of American industry provided redundancy and flexibility that smaller industrial bases could not match. The Norden bombsight exemplified this resilience. When component shortages threatened production in 1943, manufacturers identified alternative suppliers, modified designs to use available materials, and maintained output with minimal interruption. Japanese attempts to develop indigenous alternatives to the Norden revealed another critical disadvantage. American engineers had been refining bombsight technology since the 1920s, building upon 2 decades of experience with gyroscopic instruments and mechanical computers. The Norden Mark 15 represented the culmination of continuous development, incorporating lessons learned from earlier failures and incorporating improvements suggested by operational testing. Japanese engineers, starting effectively from scratch in 1942, could not compress this learning curve into the compressed timeframe available. The simplified Type 1 Model 2 bombsight that finally entered limited production represented a pragmatic acknowledgement of reality. Japanese engineers had abandoned any attempt to match the Norden's capabilities and instead focused on creating something, anything, that could be produced in meaningful quantities with available resources. The result functioned, but barely exceeded the performance of conventional manual bombsights. The gyroscopic stabilization helped, but without the automated computation and autopilot integration that made the Norden revolutionary, the Japanese version offered only marginal improvements. Combat reports from the few Japanese bomber crews who used these simplified bombsights confirmed their limited utility. Under ideal conditions, flying straight and level approaches against lightly defended targets, the sights performed adequately. Under realistic combat conditions, with the bomber maneuvering to avoid fighter attacks and anti-aircraft fire, the system's limitations became obvious. Bombardiers reported that they often achieved better results, reverting to manual methods rather than struggling with temperamental equipment that demanded constant adjustment and calibration. The irony was not lost on Japanese military planners. By the time indigenous bombsight production finally began in early 1945, Japan's strategic situation had deteriorated so completely that precision bombing capability mattered little. American air superiority over the home islands was absolute. B-29 superfortresses flew daylight missions with minimal losses, using their Norden bombsights to devastate Japanese cities and industrial facilities. Japanese bombers, when they managed to fly at all, operated primarily at night or in weather conditions that made precision bombing impossible regardless of equipment quality. The few Japanese aircraft that still ventured into combat by mid-1945 increasingly served as kamikaze weapons, where bombing accuracy became irrelevant. The sophisticated bombsight technology that Japanese engineers had struggled for 3 years to replicate no longer mattered when pilots deliberately crashed their aircraft into targets. This grim evolution represented the ultimate admission of industrial defeat. Japan had lost the technology race so completely that it abandoned technology entirely, relying instead on suicidal courage to compensate for material inadequacy. American engineers, meanwhile, had continued improving the Norden throughout the war. The Mark 50 that equipped B-17 seconds and B-24 seconds over Europe represented the baseline. Modified versions for the B-29 incorporated refinements based on combat experience. Radar integration allowed blind bombing through cloud cover. Improved gyroscopes extended operational periods between calibrations. Enhanced computing mechanisms provided more accurate trajectory calculations at the extreme altitudes B-29 seconds operated. Each improvement emerged from systematic testing, field feedback, and continuous development programs that Japanese industry could not support, while simultaneously fighting for survival. The contrast extended to maintenance and support systems. American bomber bases featured specialized bombsight shops staffed by trained technicians equipped with testing equipment, spare parts, and detailed maintenance manuals. These facilities could diagnose problems, replace defective assemblies, and recalibrate instruments to specifications. The entire system was designed around the assumption that complex equipment would require regular maintenance and that this maintenance could be performed by personnel with standardized training using standardized procedures. Japanese bomber units, operating from bases that often lacked basic supplies and spare parts, could not provide comparable support. When bombsights malfunctioned, which they frequently did, crews often had no recourse beyond attempting field-expedient repairs with inadequate tools and no replacement parts. The sophisticated equipment that might have given Japanese bombers precision capability became instead another maintenance burden that already overstretched ground crews struggled to address. The documentary evidence that survived the war tells the story of Japanese frustration in stark terms. Technical reports from 1943 and 1944 repeatedly cite manufacturing difficulties, quality control problems, and performance shortfalls in domestically produced bombsights. Engineering change proposals suggest modifications to simplify production, reduce material requirements, or eliminate problematic features. The trajectory is unmistakable. Each iteration of Japanese bombsight development reduced sophistication further, accepting diminished capability in exchange for some hope of actually producing equipment in usable quantities. By comparison, American technical documentation from the same period shows continuous refinement and enhancement. Production specifications became more demanding, not less, as manufacturers achieved greater control over their processes. Quality standards increased rather than decreased. The number of variants expanded to meet specialized requirements for different aircraft and missions. This progression illustrated the fundamental difference between an industrial base operating at the limits of its capability and one operating well within its capacity, with room to expand and improve. The human cost of this industrial disparity extended far beyond the immediate military implications. Japanese bomber crews, flying missions with inadequate equipment against an enemy with overwhelming material superiority, faced suicide odds regardless of their skill or courage. American bomber crews, despite facing fierce resistance over Germany and Japan, benefited from equipment that gave them genuine tactical advantages and increased their chances of survival. The Norden Bombsight, even with its real-world limitations and combat performance that fell short of pre-war promises, still represented a significant capability that Japanese crews simply did not possess. The post-war interrogations of Japanese aviation engineers and military planners revealed the depth of their understanding about what had gone wrong. They acknowledged that copying the Norden had proven impossible, not because they lacked comprehension of the principles, but because they lacked the industrial infrastructure to implement those principles at scale. They recognized that American mass production methods represented a fundamentally different approach to manufacturing that Japan had never developed. Most significantly, they understood that changing this would have required transforming Japan's entire economic and industrial structure, a task impossible to accomplish while simultaneously fighting a losing war. These admissions carried particular weight because they came from engineers who had spent years attempting the impossible. They had examined captured Norden bombsights component by component. They had documented every mechanism, every tolerance, every design feature. They had attempted to replicate what they found using Japan's best facilities and most skilled workers. The failure was not from lack of effort or inability to understand. It was from fundamental limitations in industrial capability that no amount of determination could overcome in wartime. The lessons learned from this failure would shape post-war Japanese industrial development profoundly. When Japan rebuilt its manufacturing sector after 1952, engineers who had struggled to copy American equipment during the war deliberately adopted American production methods. They studied not just American products but American manufacturing systems. They implemented quality control procedures borrowed from American industry. They organized production lines around standardization and interchangeable parts. The transformation took decades, but eventually made Japan a global leader in precision manufacturing. But that transformation came too late to affect the war's outcome. During the conflict, Japanese industry's inability to match American manufacturing sophistication meant that captured American equipment remained superior to anything Japan could produce domestically. The Norden Bombsight, that 50-pound assembly of gears, gyroscopes, and precision optics, perfectly symbolized the industrial gap that doomed Japan's war effort from the start. American factories could produce such instruments by the thousands, install them in bombers rolling off assembly lines by the hundreds, and support them with supply chains that stretched across oceans. Japanese industry struggled to produce even simplified copies in quantities too small to matter. The B-29 superfortresses that appeared over Japan in late 1944 carried Norden bombsights that represented the fourth generation of the basic design. Each represented thousands of hours of engineering refinement, produced in factories employing tens of thousands of workers, supported by supply chains connecting hundreds of specialized suppliers. The bombardiers who aimed these instruments had trained for months in programs that processed thousands of students annually. The entire system, from initial design through operational deployment, embodied industrial capability that Japan could not begin to match. When those bombardiers looked through their Norden sights at Japanese cities below, they were seeing through instruments that Japanese engineers had examined, measured, and attempted to copy years earlier. Those captured bombsights, painstakingly documented in Tokyo laboratories, had taught Japanese engineers what they already feared was true. American industrial supremacy was not a matter of individual technological breakthroughs that could be copied. It was the product of an entire industrial ecosystem that had evolved over decades, building capability upon capability until the gap became unbridgeable. The story of the Norden bombsight in Japanese hands is ultimately not a story about one piece of equipment or one failed development program. It is the story of an industrial nation discovering, through direct examination of enemy equipment, that it had fundamentally misjudged the opponent's capabilities. Japan had entered war assuming that American industrial advantages could be offset by superior fighting spirit, better training, and tactical innovation. The captured Norden bombsights demonstrated that the industrial gap was too vast to bridge through intangible advantages. Modern war had become a contest of production capacity, and in that contest, Japan had been overmatched from the first day. The engineers who had examined those captured instruments understood this truth earlier than most. They had held in their hands proof of American manufacturing sophistication. They had attempted to replicate what they found and failed despite their best efforts. They knew, years before the general population, that Japan's industrial base could not sustain a war of attrition against the United States. The Norden Bombsight had taught them this lesson, one precisely machined component at a time, through the simple reality that what they could document and understand, they could not build in the quantities needed to matter. This knowledge carried its own burden. Engineers and technicians who spent the war years struggling with impossible tasks understood that their failures stemmed not from personal inadequacy, but from systemic limitations beyond their control to fix. They worked extraordinary hours, applied enormous ingenuity, and achieved remarkable results given available resources. But remarkable given circumstances was not enough when facing an opponent whose circumstances were fundamentally superior. The captured American equipment they studied reminded them daily that individual brilliance could not compensate for industrial inadequacy measured in orders of magnitude. In the final accounting, perhaps this was the Norden Bombsight's most important contribution to the Pacific War. Not the bombs it delivered or the targets it destroyed, but the lesson it taught to those who examined it most carefully. Japanese engineers who studied captured Nordens learned that modern industrial war was won in factories as much as on battlefields, that sophisticated weapons required sophisticated production systems, that individual craftsmanship, however refined, could not match systematic mass production when the contest was measured in thousands of units rather than dozens. These lessons, learned too late to affect the war's outcome, would prove invaluable in the post-war decades when Japan rebuilt its industrial base on principles closer to those that had made the Norden Bombsight possible. The device that Japanese engineers could not successfully copy during wartime became, in a sense, the template for Japan's post-war industrial transformation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.